Okay, let's take a look at our old exam. First question. We have some acid-base reactions here to look at. We have one equivalent of hydrochloric acid. We know this is a strong acid. So the other molecule has to be the base. But looking at our base, there are three basic sites. There's three atoms that's got lone pairs of electrons, so all of those can be a base. Now we need to figure out which one is going to go and get the proton off the acid. So if you recall, our basicity increases as you go up a column and as you go from the right to the left. This is basicity, or increasing base strength. Oxygen is above the sulfur on the periodic table. So oxygen is more basic than the sulfur. But the nitrogen is to the left of oxygen, so nitrogen is more basic than the oxygen is. So the nitrogen atoms are most basic there in that molecule. It's the nitrogen that is going to go and get the proton off of the acid. Remember, there is partial positive charge on that hydrogen because the chlorine is more electronegative. There's partial negative on the chlorine. So that lone pair of electrons is attracted to that partial positive of the hydrogen. So we're forming a bond between that nitrogen atom and the hydrogen. Now let's get our charges on. Initial tail becomes more positive charge, so that nitrogen will now have a full plus charge. The chlorine, if you want to show it, you don't have to. The chlorine has a negative charge. That's what balances the charge out with it. But there is our product. So the nitrogen is the most basic. That's what goes and grabs the proton off the acid. Looking at our next one. We have the same type problem here. We have hydrochloric acid, HBr. HBr is even a stronger acid than hydrochloric acid, so this is a strong acid. So the other molecule has to be the base. But we've got two main basic sites. Either oxygen could go and get the proton off the acid. You have to figure out which one is more basic. Now it does matter. They're both oxygens. But if we were to take a look at the resonance, the carbonyl has resonance up onto the oxygen. This one has no resonance, so let's look at our resonance structure. There's your resonance structure. So we know the real structure is a hybrid of all of our resonance structures. So with this oxygen, part of the time it's a full negative, part of the time it's neutral. So there's a big partial negative on that oxygen. This carbon would have a big partial positive. Now the other oxygen does have some partial negative because of electronegativity, but it's just that inductive effect is all that's giving it a partial negative. So I'm going to put it a tiny partial negative. This is a big partial negative. It's got the electronegativity, inductive effect, but it's also got the resonance that's putting negative charge up on the oxygen. So big partial negative on the carbonyl oxygen. So that's what will go and get the proton off of the acid. That's what's attracted to that partial positive of the hydrogen. It's the carbonyl oxygen. So I mentioned, we covered this in lecture, when you have a choice between a carbonyl oxygen and something else, it's normally that carbonyl oxygen that's what's going to go and get the proton because of that resonance. Take a look at the next one. So again, the most difficult part's figuring out what is the acid, what is the base. Let's see what we can come up with here. If you examine the two compounds, one of them has something that I love to see. I've mentioned this many times. Lithium, sodium, potassium, maybe even magnesium. But especially that lithium, sodium, and potassium. You see those have a full, those metals have a full plus charge, and then whatever is else attached has a full negative charge. And so I see one of those sodiums there. Full plus charge on the sodium, full negative charge will be on that carbon. This is a strong base. Very strong base. So it's that carbon, there's a lone pair on the carbon. That's going to be our base. This is going to come and grab the most acidic hydrogen that we have in the other compound. So this has to be the acid. Doesn't have a choice. Now let's examine and see where the most acidic hydrogen is. Well, we've got hydrogens on carbons, but we've got hydrogen on oxygen, hydrogen on oxygen. You're more acidic on the oxygen because of the periodic trend. But I've got two of them. Got to make a decision. We've only got one of these. Which one is more acidic? So we've got two alcohols. This one has no resonance. This oxygen has resonance into the phenyl group. This one is more acidic. pKa of this one is about 10. pKa of this one is in that 16 to 18 region. This is just a normal alcohol. So this is our most acidic hydrogen. That's what's going to react with the base. The base, that CH3, is going to come and grab the hydrogen off the acid and will leave the electrons there on that oxygen. Put your charges on. The initial tail becomes more positive by charge, so that CH3 grab the hydrogen, that carbon now be a CH4, and that will be neutral. And the oxygen final head becomes more negative by charge, so that oxygen has a full negative charge. You make a CH4, make methane. Methane just bubbles out. It's a gas, but there is our main organic product. So that base went and grabbed the most acidic hydrogen that we had. That's the most acidic hydrogen. Take a look at the next one. See what we can identify, our acid or our base. DCl, the D is a deuterium. We know it's going to react just like HCl. That D, the deuterium, acts just like a proton. No difference, it's just an isotope of hydrogen. So HCl, you know that's a strong acid, so DCl is also a strong acid. So if this is going to do anything, the other molecule has to be the base. So the base goes and gets the proton off the acid. Now let's look and see if we've got what the basic side is. What can go and get the proton? Normally we like to have lone pairs, like up here. A lone pair goes and gets the proton. If you can't find a lone pair, we don't have a lone pair of electrons anywhere. If you can't find a lone pair, then we can use double bonds and triple bonds. You use lone pair first. That's the easiest thing because you don't have to break a bond. Here we're going to have to break a bond. We're going to use the double bond to come and grab the proton, which is not proton this time, it's deuterium. There's partial negative charge on the chlorine, partial positive on that deuterium. So we take a pair of electrons out of the double bond to come and grab the deuterium, and then we will leave our electrons on the chlorine. One of those two carbons here of the double bond gets the deuterium. It does not matter which one you put it on. One of those two carbon gets the deuterium. The initial tail becomes more positive charge. So the other carbon, one carbon gets the deuterium, the other one will be left with a plus charge. So there is using an alkene as a base. We went through several organic molecules as a base in class, but I did not go through an alkene. We covered several other functional groups, but an alkene or an alkyne can also be a base. Now the chlorine got kicked off. You have a chlorine anion. If you want to show that, you can. If you don't, you don't have to. So there's our product. Now this can go on and react further, so I would accept either one because we talked about carbocations. That is a Lewis acid. Chlorine anion got like lone pairs. This can be a Lewis base. So this can add to the carbocation. If you do that, then here's your product. So this is actually what actually happens. It will go all the way to this, but I would have accepted either one because that's kind of tricky to do two of them in a row there. But that is what happens. We have an acid base followed by another acid base. Looking at the next one, let's see what we can identify. Got to figure out what's the acid, what's the base. Iron chloride. That iron chloride, 3 chlorines around the iron. Those halogen atoms are all pulling electrons away from the iron. Partial negatives on all the chlorines. Big old partial positive on that iron. This is a Lewis acid. Lewis acids will have full plus charges or large partial positive charges. So we talked about our Lewis acids always have some kind of metal. I'll use M for a metal. And they have several halogens around them. Maybe 2 or maybe 3, or sometimes they even have 4 around some metal. It's always halogens, fluorine, chlorine, bromine, or iodine around a metal. That's going to be an acid, Lewis acid. Okay, so Lewis acid, the other molecule has got to be the base. So something's going to go and attack that iron. It's got the partial positive charge. We're going to get a lone pair of electrons, if at all possible. If not, then you can use a double bond, but we'll use the lone pairs first. That's the easiest thing, where we don't have to break a bond. You can use double bonds and triple bonds, but we prefer lone pairs. Now I've got 2 oxygens with lone pairs, and one of them's a carbonyl oxygen. We just talked about that here in the previous problem. If you do resonance, there's a huge partial negative charge on this oxygen because of resonance. This one would actually have partial positive charge if you do the resonance. So it's the carbonyl oxygen that will go and add to the iron. We're not going to kick anything off because the iron only had 6 electrons to start with. And if we give it 2 more, then that gives it 8. Now let's get our charges on. Initial tail becomes more positive by charge, so that oxygen has a full plus charge. Final head becomes more negative by charge, so the iron has a negative charge. We're finished. This was a Lewis acid base reaction. Our next one, again, let's look for which one is the acid, which one is the base. There's one of those first column metals, first group metals, group 1 metals, full plus charge on the sodium. Sodium, group 1, sodium, lithium, potassium, those are going to be good. Plus charge on those, negative charge on whatever else is out there. So full negative on the nitrogen. These are going to be strong bases. This is a strong base. This is going to have to be the acid. Now, we need to find our most acidic hydrogen. We have hydrogens on sp3 carbons. We have hydrogens on sp2 carbon here. And we have a hydrogen on the sp hybridized carbon. Your most acidic on the sp hybridized carbon. This has a pKa of 25. So our base is going to come and grab this proton that's on the alkyne. We'll leave the electrons there on that carbon. So there is our product. Now NH2 grab the hydrogen. If you want to show it, you'd have NH3. And the sodium floats along and balances the charge out. It would sit there and balance the charge out with a negative. But there is our organic product there that I've got circled. That's what we're looking for. Let's examine our next one. We need to identify the acid and the base. The base always goes and grabs the proton off the acid. Got one of those, we have one of those group 1 metals. Got a sodium there, full plus charge on the metal, full negative charge on whatever else is out there. That is a strong base. The other molecule has to be the acid. Now we need to find the most acidic proton. We have hydrogens on the carbons, hydrogen on nitrogen, hydrogen on oxygen. You get more acidic as you go across a row from the left to the right on the periodic table, so the most acidic hydrogen is on the oxygen. So our base will come and grab that proton, and we'll leave the electrons there on the oxygen. So OH grabs a hydrogen, that would make a water molecule, and then we are left with this here as our organic molecule. Again, sodium would balance the charge out if you want to write the sodium there. Yeah, it's just a spectator ion. The final head becomes more negative by charge, so that oxygen has a full negative charge on it. Our last one here on the reactions, this is a reaction that we just talked about this morning in lecture. This is a hydrogenation. A hydrogenation reaction. It is not an acid base, it is a hydrogenation. So let's look at how that works. The palladium is our catalyst. We have this under high pressure. The palladium's the catalyst. It's going to coordinate with the hydrogen molecule. Let's just draw that hydrogen out. There it is, drawn out. So the palladium coordinates there to the double bond and to the hydrogen. And we essentially just move the electrons around the cyclic array. You're going to take the double bond, come out and get a proton, electrons in the hydrogen bond. This goes to the other carbon of the double bond. And this will turn that alkene into, that side into an alkane. We said we can also do alkynes. You can do hydrogenation of alkynes. So this was just a hydrogenation reaction. This was not an acid-base reaction. Our next one here, this one asks for the mechanism. Well, I gave you the full reaction. And just asked you to provide the curved arrows that show the flow of electrons. So HCl is our strong acid. The other molecule has to be the base. And the base always goes and attacks the acid. It's the oxygen, one of those lone pairs, are going to go grab the proton off the acid, and the electrons in the hydrogen-chlorine bond, those get left on the chlorine. There is our mechanism. Now you only have to show the mechanism when I ask for it, but it doesn't hurt anything to show it on the other reactions. Then I can give you partial credit if you were to mess the product up somehow. I can at least give you some partial credit if you got the arrows right. So again, you only have to show the mechanism, the curved arrows, on the question where I asked that. On any of the others that we had there back earlier, I just said complete the following reactions or give the major product. That's all you have to do. You don't have to show the mechanism, but it doesn't hurt anything. I can give you some points for that. Take a look at our next one here. Putting some molecules in order of increasing acidity. So the first thing that we need to do before we start trying to put them in order, before you start comparing molecules, you need to first find the most acidic hydrogen within each molecule. So let's look at each molecule and then we'll start comparing. So looking here at the first one, so we're looking at acidity, looking at protons. Let's see what we have. We've got hydrogens on carbons and a hydrogen on a nitrogen. At periodic trend, you get more acidic as you go across a row of the periodic table. So we're more acidic on the nitrogen than we are any of the carbons. This is our most acidic hydrogen on that nitrogen. Let's take a look at the next one. We have hydrogens on carbons here in the ring, hydrogen on carbons out here. And that's all we got, hydrogens on carbons. Some of them are on sp3 carbons, some of them are on sp2. You're more acidic on the sp2. So this is our most acidic hydrogens, the ones that are on those carbons. It's the best we got. Looking at the next one, hydrogens on carbons, hydrogen on nitrogen. You're more acidic on the nitrogen. Periodic trend. The last one here, hydrogens on carbons, hydrogen on oxygen is the most acidic. Periodic trend. Now we can start comparing. We've found the most acidic hydrogen within each molecule, and now let's compare those. Hydrogen on nitrogen, hydrogen on carbon, hydrogen on nitrogen, hydrogen on oxygen. The least acidic is on the carbon. So it said in order of increasing acidity, it said put the least acidic first. So B is the least acidic. Greater acidity than B. Well, any of them is greater than that. So looking at that, we got tie there with nitrogen. Hydrogen on nitrogen, hydrogen on nitrogen. We'll come back to that. Let's go to the oxygen. That's our most acidic. So I'm going to put that one down here at the end. Your most acidic is on the oxygen. Periodic trend. But we have a tie with A and C here. So periodic trend doesn't work. So what I said is look for periodic trend first, look for hybridization next, then resonance, and last look for inductive effects if you have a tie all the way down. So we had a tie here on nitrogen with the periodic trend. Let's look at hybridization. That's sp3 hybridized, that's sp3 hybridized. That doesn't help us. Let's look at resonance. Resonance, this nitrogen has resonance. Any of them that's got a lone pair can change their hybridization, so it can change to sp2 and then it can do resonance. This one has no resonance. You have an sp3 carbon that is in between. sp3 carbons act as a roadblock, so that nitrogen has no resonance. This one is more acidic because of the resonance. So we have C, and then A, and finally D is the most acidic. There's our order. B, C, A, D. So again, before you start comparing molecules, find the most acidic within each structure. do the same thing here on the next one. We're going to first identify the most acidic proton, most acidic hydrogen within each molecule, and then we'll start comparing molecules. If we compare these, before we compare, like I said, find the most acidic within each structure before you start comparing. Here in the first structure, hydrogen's on carbons, hydrogen on oxygen. That's our most acidic hydrogen. It's on the oxygen. You look at the next one, hydrogen on carbon, hydrogen on oxygen. You're more acidic on the oxygen. Next one, same thing. We're more acidic on the oxygen. Last one, same thing on the oxygen. Okay, we found the most acidic hydrogen within each structure. Now we can start comparing. If you look at all of them, they're all hydrogens on oxygen atoms. We have a tie all the way down. Periodic trend's out the door. We're done with periodic trend. Hydrogen on oxygen, most acidic. We're finished with periodic trend. Hybridization. Hybridization is the same on all those oxygens. Resonance. Now you may have already noticed these. These are carboxylic acids, all except for the last one. These all have resonance. Resonance, 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 no resonance. This one is just an alcohol. The other three are carboxylic acids. So we've got one figured out, the alcohol, no resonance there. That's less acidic than the carboxylic acids. So D is the least acidic. Did say in order of increasing acidity, so said to put the least acidic first. That's the order of increasing acidity. So we've gotten rid of one of them, but we've still got three more, and they're all carboxylic acids. So we've looked at resonance. We went down our list: periodic trend, hybridization, resonance. The only thing that's left now is inductive effects. That's the only thing that could possibly tell the difference in these. Now, here we have a bromine. Bromine can pull inductively through the bonds. It is an electronegative atom. So it pulls through the bonds and away from that hydrogen. It's pulling through 4 bonds. This one has no bromine, so we have no additional inductive effects. You do have inductive effects because of the oxygen, but those are all have that. We're looking for something different. This one has a bromine, so it can also pull. But if you look at it, it's pulling through 5 bonds. It's having to pull a further distance. So the least acidic out of the 3 is the one without the bromine. That would be next. An additional bromine, that bromine is giving an additional inductive effect, so that makes those more acidic. And the closer it is to your proton, the more it can pull. I used the example of a magnet on the refrigerator. The closer the magnet is the refrigerator, the more you pull that you get. So this one here is getting more pull. This one is more acidic than having to pull through 5 bonds. So C is next. And then the most acidic would be in A. So our next one is asking about basicity. We're looking at base strength. Now, base strength is just the opposite of acidity. Now there's a couple different ways that we can work this. I'll show you both of them here. Looking at these, 3 of them have got a full negative charge, 1 of them is neutral. Full negative generally means those are going to be more basic. Those strongest bases have a full negative charge, just like the strongest acids. You're looking for as much partial positive or a full positive as possible. So these with the bases here, with full negatives, those are going to be more basic. So the least basic right off the bat is the neutral one. That is C. Looking here at the others, so the full negative is on the oxygen. That's our basic site. And we have on oxygen and on the sulfur. Basicity, as far as periodic trend, basicity goes up a column and from the right to the left. So the oxygen is right above sulfur on the periodic table. So you're more basic on the oxygen than you are the sulfur. So that negative charge on an oxygen is going to be more basic than a negative charge on a sulfur. So the sulfur here is next, as far as the least basic. Now we have a tie with the other two. It's negative charge on oxygen, negative charge on oxygen. Looking at those. This one, the difference between them, this one's got fluorines. Fluorines pull inductively, so this is pulling through the bonds. That's pulling electrons away from the oxygen. Now inductive effects, that helped acidity. It made things more acidic. It hurts basicity. It will make things less basic. Remember, your bases generally were just the opposite of acids. So this inductive effect is making that oxygen less basic. It's pulling the electrons away from it. That oxygen needs as many electrons as possible, as much negative charge as possible to go react with some acid. We want it to go react with an acid. So the more negative charge it has, the more it's attracted to some acid. But the fluorines are pulling some of that charge away. So that makes this less basic than that one. That one's going to be the most basic over there. D is. So we've got A and then D. So there's our order. D is the most basic out of the bunch. Now there is another way. We discussed this when we covered basicity. You can look at the conjugate acid of all of these. So if we were to react these with some proton, look at the acids, the conjugate acid, and then just take the opposite. Now if we look at these, our acid is hydrogen on an oxygen, hydrogen on sulfur, hydrogen on nitrogen, hydrogen on oxygen. Now if you notice, all of those are neutral except for this one. This one's got a full plus charge. Full plus charge is normally the most acidic. Maybe not always, but oftentimes they're going to be the most acidic. But if we look at these, hydrogen and oxygen, this is an alcohol. Alcohols typically have a pK of about 16 to 18, but we've got 2 alcohols. The fluorines make this one a little bit more acidic than a normal alcohol. So So you got 2 fluorines, it's going to drop it just a little bit. So maybe this one is, I don't know the exact number, maybe this one is about 14 instead of being that 16 to 18 region. This one's about 16 to 18. So that makes this one a little bit more acidic than that one. Periodic trend, you get more acidic as you go across a row and down a column. So SH is going to be more acidic than an OH. And like I said, we're typically the most acidic when you have a full plus charge. So this is our strongest acid. Now, we just take the reverse order for the bases. Since we protonated, look at the conjugate acid, we've got the order, and we just take the opposite. So the strongest acid was C, so it would be the least basic. The next strongest acid was B, and it would be the next in the basicity there, the next least basic. And then the other two were alcohols. This one was a stronger acid than that alcohol, so that means just the opposite. This will be a weaker base than that one. This was the weakest acid of the group, but it will be the strongest base. So you can look at that conjugate acid, or you can maybe figure that out just looking at the negative charges there before. So I showed you 2 ways to work that. Okay, I am going to stop there for just a second on you here, because last time, we got cut off. My camera will only record for 1 hour, so I'm going to stop it right there. I'm through 3 pages, got 2 more pages to do, so I'm going to film this in 2 parts. So that's the end of part 1.